Why do all the planets orbit in the same plane? There are many planetary systems like ours in the universe, with planets orbiting a host star. Our planetary system is named the Solar System because our sun is named Sol, after the Latin word for sun, solus, and anything related to the sun we can call solar. As soon as they began to observe the night sky, astronomers found that Mercury, Venus, Mars, and basically all the other solar system planets orbit in almost coplanar orbits. How is that possible? An explanation for this was needed. As of today, we think the reason is the following. The orbits of the planets are coplanar because during the solar system's formation, the planets formed out of a disk of dust that surrounded the sun. Because that disk of dust was a disk, all in a plane, all of the planets formed in a plane as well. But let's see this in more detail. Ladies and gentlemen, welcome to the world of planetary formation. According to the most recent study, all exoplanets are different, and there are plenty of them out there. On some exoplanets, it rains diamonds. Some of them have an iron core. Some others have an ice core. Exoplanets may rotate clockwise or anti-clockwise. They might be rotating faster or slower, and they can be big in size or small. Some of them could be habitable with vast oceans on their surfaces. Some others, being really close to their host star, may be in a tidal destruction process that heats them up, causing strong volcanic activity. If there's one thing we understood about planets, is that they're all different from each other. But all of them have one thing in common. All planets and exoplanets were born in an environment known as a circumstellar disk around their host star. How is that possible? Let's start from the beginning. We'll use our solar system as an example. A star forms as a consequence of a dynamical collapse of a giant cloud of gas. Most likely, this huge cloud of gas was in a really unstable equilibrium state. The smallest perturbations in the gas could derive a gravitational collapse, under which the molecules become denser and denser, and the cloud shrinks as a whole. It is probable that the event that triggered the collapse was external to the cloud itself, otherwise an equilibrium between its parts. Scientists have advanced the hypothesis that it may have been the explosion of a nearby supernova, that is, a star of great mass that has reached the end of its life and explodes, expelling its entire atmosphere into space. The silent shock wave would then have given the initial thrust to the cloud. Thus, the death of a star can generate the birth of another star. The heat and energy from this collapse create pressure that, as time passes by and the cloud gets dense enough, counterbalances the effect of gravity, holding the system together. When a hydrostatic equilibrium is reached between these two forces, gravity and pressure, the star is basically born. Stars are big and hot balls of gas created by the collapse of huge clouds of initially cold gas. We think the great majority of the stars were born like this, and our sun is no exception. What really happens afterward is a bit more uncertain, but we know for sure that at this stage there's a circumstellar disk surrounding the star, and the material keeps free-falling around the star. We say around because free-falling matter does not fall in a straight line towards the center, but rotates around in even tighter spirals. The rotation of the sun and the planets around their axis, as well as the revolution of the planets and other bodies around the sun, is precisely the remnant of this initial whirlpool. At the periphery of the cloud, far from the star, the remaining material continued to rotate around the center. Then something simple, yet fantastic happened. The material settled into a thin disk under the effect of this rotation. This is a pretty basic physics concept that we are used to. Take your washing machine, for example. You fill it with dirty clothes, add the bleach, and press start. The laundry has begun. Now you observe the clothes rotating, basically orbiting around the center of the washing machine. As they rotate, they are pushed towards the walls, and this is the effect of the centrifugal force. But if you look closely, they are not pushed in random directions. They're not randomly spread out. They are rotating in some sort of a disc-shaped region. Basically, your clothes are orbiting in almost the same orbital plane. This is what billions of years ago happened to the material surrounding the sun. The material thinned into a disk as a consequence of the conservation of angular momentum, and some small bodies called planetesimals started forming as a consequence of collisions. Subsequent aggregations then led to the formation of the planets as we know them. Even today, the major bodies of the solar system revolve around our star on almost the same plane called the ecliptic. Well done! This is the simplest and most elegant way to answer the initial question: why do planets in the solar system orbit in the same plane? But our solar system is not only made of planets. If you take a telescope, you can clearly see that other small bodies populate our planetary system. These are asteroids, frozen bodies, and dust. Scientists think that they are the oldest remnants of the solar system formation, that is, the fruit of primordial aggregations that failed to evolve into planets. Their orbits, more inclined than the ecliptic, testify precisely to the fact that these bodies were excluded from the main formation mechanism along the rotation disk. Most of this ancient space rubble can be found orbiting the Sun between Mars and Jupiter within the main asteroid belt. Asteroids range in size from Vesta, the largest at about 329 miles or 530 kilometers in diameter, to bodies that are less than 33 feet or 10 meters across. The total mass of all the asteroids combined is less than that of Earth's moon. Some asteroids go in front and behind Jupiter. These are called Trojan asteroids. Asteroids that come close to Earth are called near-Earth objects, NEOs for short. NASA keeps a close watch on NEOs because they could be potentially dangerous. Space agencies are currently looking for ways to deflect the trajectory of an asteroid in order to defend our planet. There's actually an entire field of astrophysics and engineering devoted to planetary defense. For instance, the DART mission, launched in November of 2021, will impact an asteroid on September 26, 2022, as an orbit demonstration of asteroid deflection. Basically, DART will impact the asteroid Didymos to adjust its speed and path. DART will be the first ever space mission to demonstrate asteroid deflection. We can't wait to see if it works. Hey, if you're still here, it means you're really enjoying the video. Why don't you subscribe now and press the bell notification? So we understood that as a rule of thumb, planets orbit in the same plane. But let's take a look at our solar system. Do they all really share the same plane? As Earthbound humans, we have adopted the plane in which the Earth moves around the Sun as our reference plane for the solar system. If the Sun's path is observed from the Earth's reference frame, it appears to move around the Earth in a path that is tilted with respect to the spin axis at 23.5 degrees. This path is called the ecliptic. It tells us that the Earth's spin axis is tilted with respect to the plane of the Earth's solar orbit by 23.5 degrees. With this convention, if we put ourselves on the ecliptic, the Earth has an orbital inclination of 0 degrees, and the orbital inclinations of the solar system bodies are measured relative to this. For example, Mars has an orbital inclination of 1.8 and Mercury of 7.0. As you can see in this picture, planets make nice circular orbits around the Sun. However, the dwarf planet Pluto's orbit is very different. It's highly elliptical, traveling around the Sun in a squashed circle, and Pluto's orbit is highly inclined, traveling at an angle of 17 degrees. This strange orbit gives Pluto some unusual characteristics. For example, it orbits so widely that it can switch places with Neptune, orbiting closer to the Sun. The last time this happened was on February 7, 1979. Pluto remained closer to the Sun than Neptune until February 11, 1999, and the previous time it happened was back in the 1700s. With its low mass, Pluto's orbit is actually quite chaotic through its interactions with Neptune. This means that it is not easy for astronomers to predict where Pluto will be in the next millions of years, because the uncertainties mount up and it's impossible to know where it'll be in the far future. To sum everything up, we could say that what we observe in the universe today is the result of physical processes that happened over a timescale of billions of years. On one hand, simple physical explanations can be given to understand why both the planetary systems and other objects like spiral galaxies have the form of a disk. On the other hand, though, scientists know that, unfortunately, we live in a non-deterministic universe, which is rather chaotic. This means that the slightest perturbation in a system can lead to unpredictable results. Therefore, we can have planets orbiting in highly inclined orbits like Pluto, or strange features of the fabric of a galaxy of a moon-planet system. For example, did you know that the moon is slowly drifting away from Earth? The effects of chaos, though, are only detectable over very long timescales. I mean, chaotic events keep happening all the time, but their effects are basically negligible over human life timescales. This is good for us humans because, given our short life compared to the age of the cosmos, we can treat the phenomena as quasi-static and pretend, even if just for a second, we can't predict the behavior of the universe. That's all for this video. What do you think about it? Let us know in the comments below. And if you enjoyed the video, don't forget